Graz University of Technology to present his work on handling temporal correlated noise in large-scale global GNSS processing.
Thank you very much for the introduction. I'm DUMITRASCHKEWITZ from University of Technology, Graz, and I'd like to give a bit too loud, sorry. And I'd like to give a short introduction on how we handle temporal correlations in our global GNSS process. Why do we actually do this? After participating in the Reprocessing Campaign, we found several fields where we can have improvements. And one such field is the usage of a more sophisticated stochastic modeling. Because so far in our in-house software groups, which some or some may not know, we only use an elevation-based weighting model. So we have a very simplistic modeling of the observations between phases and between codes. And we were not really happy about that. We wanted to improve about that. So one thing that is definitely known about the observation noise of the GNSS observations is that it is not white noise behavior, as we assume with an elevation-based weighting, as is shown in several researches. And there's barely any research regarding the stochastic modeling impact of temporal correlations on global GNSS, but there are already research for, let's say, normal GNSS proceeding, which uses, for example, variance component estimation or modeling of post-fit residual strategies. And I'm just going to skip this very fast because I think everyone in here knows the formula about it. But we at TUG apply the raw observation approach. This means we use every observation as observed by every receiver, and we don't do any linear combinations or any different strategies. And this means that in our processing strategy, since we use a distributed memory system, we apply so-called accumulation of the normal equations. This means we use our design matrices, which are nothing else for one epoch between a receiver and a satellite, and we accumulate this over all epochs, as is shown in the top. And for one epoch, for example, we can say that our design matrix then looks as a temporal part, which is basically only the clock parameters for the global GNSS processing. For PPP and kinematic, it will be different, of course. Then we have our receiver part, which is the station position, tropospheric parameter, calibration parameters, and signal biases, the transmitter, where we estimate orbit parameters and signal biases from the transmitter, and last but not least, the ambiguities. Using this accumulation, we get to our normal equation structure, which looks like this, where we have our kite-like structure, where our diagonal elements are nothing else but the temporal parameters, followed by non-temporal parameters such as receiver, satellites, global, which is nothing else but the Earth rotation parameters, and ambiguities. So this is a very sparse matrix, meaning it is a lot of zeros and it is easy to handle in memory, and allows for a lot of algorithms to be used efficiently in distributed memory system. For a more sophisticated stochastic modeling, though, we have to consider some things when looking at this normal equation matrix. First of all, since we use distributed memory system, we need to make sure that there is the least amount of communications between the processors. Second of all, we do not want to bloat up the matrix, because memory means more computation time, and therefore we try to limit it as little as possible. This is just a short example. For example, if we use 180 stations around, we already have a memory requirement of 100 gigabytes for the raw observation approach. So using a fully populated one is just not feasible to compute. And last but not least, the stochastic modeling needs to be working on a blockwise tiled algorithms of the normal equation matrix. So basically, there are three general ways to estimate variance components. First of all is, I think everyone knows this, I assume it is very used, the variance component estimation algorithms, which would be very attractive to use, but in raw observation approach just takes way too much memory and computation time. Then we have, for example, turbulence theory that we can use. And last but not least, we know the post-fit residual strategies, where we use the post-fit residuals and use stochastic processes to estimate the covariance behavior. And this is also the method of interest that we use. And for this, we also need to know some things about how we decorrelate our normal equation matrix. I know formulas are a bit heavy, but basically we do our decorrelation by Cholesky decomposition, where when we have our covariance matrix, we use the Cholesky decomposition and the inversion, and we have our so-called decorrelation matrix, or the inversion of the Cholesky decomposed covariance matrix. I will refer to this mostly as decorrelation matrix, even though this is probably not the right way to call it. And with this matrix, we can then transform our equation system and get rid of the of needing to compute the covariance matrix altogether. And there are some assumptions that we have to do to limit our temporal covariances. First of all, we don't take any correlation between observers and satellites into account. We don't take any correlations between phase and code into account, and only temporal correlations. The good thing is, when we look at the decorrelation matrix in blockwise manner, for any epoch I, we can just select the diagonal elements for the decorrelation, and for any other lag higher than I plus 1 or I minus 1, we can just use the upper diagonal elements, which would lead to accumulation then to looking like this. Now we come to the stochastic processes. The most prominent in the research field are the ARMA processes, autoregressive moving average processes. And they are basically the two things which are used. The AR process is probably the most prominent. The important thing about an AR process is when using it as a covariance matrix to describe it with an AR process, using the inversion of it leads to a block diagonal element when the decorrelation matrix is computed with P upper diagonal elements, which is nothing else but the order of the AR regress position. The moving average process, on the other hand, shows the complete opposite behavior, meaning that it becomes a fully populated matrix when we compute the decorrelation matrix. This becomes very prominent when we look at our normal equation structure. When we use an AR process, we just get P upper diagonal blocks additionally. For example, in an AR1 process, we get one and upper diagonal element. AR2, we get two upper diagonal elements. A moving average process, on the other hand, would fully populate the matrix and thus not make it feasible to compute. This we then set up in an analysis, hard work, I know. We basically selected a station network of 200 stations for 10 years, which was selected by mostly availability throughout the 10 years, and also additionally having as much Galileo as possible. So we used the same models and procedure as Repro 3, so we could also do some slight comparisons to our Repro 3 products. And we also separated 1 year into 60 days intervals to comply with any seasonalities in the covariances, or in the correlations, basically. Oh, cool. Misclick. Yes, and this is the station network we selected. And our impact this had, we analyzed the so-called midnight orbit discontinuities, which is nothing else but the overlapping epoch between 2 days, and this throughout the years, and computed in RMS. Now this is a bit of a heavy plot, I presume. The blue dots are nothing else but the modeling throughout 2020 with the old stochastic modeling, so with the elevation-based modeling, and so the elevation weighting. And the green dots are the one where we use the more sophisticated modeling, which we derive by the post-fit residual stochastic modeling. And what we can see throughout the year 2020, nearly all satellites improved. Especially some Galileo satellites showed more improvements, but I would derive that due to the reason that in the selected stations, from the 200 stations, I think there were, if I remember correctly, I think I do remember correctly, maximum of 70 stations had Galileo, so I assume that stochastic modeling here would have a high impact to the less dense network of Galileos, especially when it also comes together with the X signals and so forth. So this showed that we have significant improvement in our orbit RMS, and for the stations we get a similar improvements when looking at it, which is very interesting. Where we first, the two results were transformed in an independent reference frame for comparison, detrended, and then we looked at their station positions. And we can see that in the improvements were especially bigger in South America and Australia, while in Europe, where there's a way denser network, the improvements were rather limited. Of course, there are some outliers that show negative impact, but overall, the station positions have shown improvements. And overall, when we look at it, we know, so this plot here shows for the individual station position coordinate components and the orbits. And over the 10 years that we analyzed the average over all stations on over all satellites. And on average, the station RMS and the orbit RMS improved between 3 to 10%. Whereas there are 2 years where the east component in 2014 and 2015 on average actually got worse, which I'm currently investigating and not 100% sure why this occurs. Yes. And from what I can also say from this result is that as soon as we have more Galileo availability from past 2016, 2017, 2018, the improvements are a lot better than before, where we only have GPS and less available observation types. And last but not least, my future outlook, what we want to do in the future is use BeiDou additionally, then also expand the station numbers from 200 to 800, and also do with third-party software or different software PPP analysis of our products of the reprocessing and how the difference in the stochastic modeling impacted it. And with this, I'd like to thank you, and thank you.